Hey guys, thanks for tuning into CMTEQ channel. So in this tutorial, I'm going to show you how to calculate the voltage drop on an AC distributor feeder system. Now imagine this 400 meters line as a street in a particular suburb where you basically have your transformer, right? Quote unquote, a street corner transformer located at the beginning of a street, supplying power down the street to a couple of houses, right? We're taking an example of 3 houses. Now, this is a very common configuration for many electrical systems, right? In particular, we know that systems, right, that are connected in parallel, they actually receive the same voltage coming from the supply, right? In theory, that is true, but practically, that is not the case. Why? Because you're going to have a voltage drop across this line here. Now, all of these loads here, right? House 1, 2, 3, they're drawing a particular amount of current, right? So as we can see here, we've got a current flowing down here of 100 amp, okay? And there is a current here of 120 amps, right? And we've got a current of 80 amps on the last house. Now, this means in this section of the line, we've got 300 amps of current. In this section, we've got 200 amps. And in the last section, we've got the 80 amps. Now, each particular loads here got a different power factor. Now, we've got lagging power factor here, which basically means that the current is lagging behind the voltage, and the system here will have to supply more than the actual power that is being used. Okay, now these just increase the amount of current that is going to be flowing in these particular sections. Okay, and that increase the voltage drop based on the cable parameters. So this means indeed the last house here is not going to see the same amount of voltage as the first house or the in between. Now, let's say you've got a V sending VS here of 230 volt AC, right? And the last house is expected an acceptable amount of voltage drop should be about 5% of the sending voltage. So if you've got 5% of a voltage drop across the distribution line, then this one here should be getting about 223 volt AC. Okay, now that is acceptable. But in a situation where the current and cable parameters start to deteriorate, or the current being drawn is getting out of hand, and you have a voltage drop going way above the required, the acceptable 5%, and let's say 10%. So you've got a situation where you're getting like 190, for instance. Here you got 190 volt. Now this becomes a problem, okay? Because many electronics equipment, they are set to operate at a particular voltage range. So the minute you fall outside that voltage range, your equipment starts to malfunction. So to remedy that, many households make use of what is known as a voltage stabilizer. So it basically devices with a transformer that will basically take your input voltage coming with all sorts of variation from the line and stabilize it to a very solid, let's say 230 volts. So no matter what happens here, so long as the input is within the accepted range of this equipment, it might have like a minimum input of 150 volt, okay? Right? Then it will give you 230. If it drops below this 150, then it can't anymore. Well, if you get to that point, remember, you've got more problems to deal with on your line. How then we going to find a voltage drop in the system if we don't know what the sending voltage is? Because this is just an illustration. Well, do not worry about that, because a voltage drop is basically V is I times R, okay? You got your current, you need a resistance. The resistance are given here, okay? The problem statement say that there is about 0.25 ohm per kilometers and 0.125 ohm of inductive reactance. Why? Because these are cables, so it will have both these parameters, resistance and inductance within them. Okay, now this is basically what you need, all the ingredient, and you will be able to determine the voltage drop on each one of these sections. Now, before we move forward, if you found this tutorial useful, please don't forget to give it a thumbs up and subscribe to CMTEQ channel. And also, if you have any question, the comment section is open for you. I thank you so very much. Now, before we deal with the resistance conversion here, let's go ahead and first calculate our current from each one of these sections. We've are given the current magnitude, right, and the power factor here, so we can go ahead and basically do a basic conversion here. So thus here, okay, writing it in a polar form, okay, it will basically be 80, okay, 80 with an angle of 0 degree, okay, because power factor is 1. Then here it will be 120, okay, with an angle of 36,87. Okay, you can do this conversion with your calculator basically by taking the 0,8 and doing an inverse cos of 0,8. Okay, that's going to give you 36,87 basically, right? Then on this one here, you're going to do the same thing. We're going to have 100 with an angle of about 45 degree. But now remember, this is a lagging power factor, so it's going to be a negative 45, and that should be the same here, negative 36. So summing up the current from all these sections, so let's first name them. This is B, C, and D. And this point here is point A. Okay, so summing up the current, IC plus ID is basically going to be equal to 120 with an angle of negative 36,87, okay, plus 80 with an angle of 0 degree. And this is basically going to give you 176 minus 72 J. Okay, and if you convert this back to polar form, it's going to give you a value of 190,15 with an angle of negative 22.2 degree amp. So this is the sum of these two currents. Now you have to add it with this current from the second house, so that basically going to be I from B to D. Okay, so it's going to be I B D, and that's basically is going to be, we've got 100 with an angle of negative 45 plus 190,15 with an angle of negative 22,2. So adding these two current, same process we did there, you're going to get a value of basically 285 with an angle of negative 30 degree amp. So this is basically the total current combined of all these three current. Now we can go ahead and convert our resistance values. So basically we've got 0.25 ohm per kilometer of resistance and the reactance of 0.125 ohm per kilometer. So the impedance, which is a combination of resistance and reactance, is going to be, for the 100 meters section, it's going to be Z, okay, Z 100 meters, that's going to be R 100 plus XL 400 meters as well. And this is basically going to be the conversion. So you have to take the 100 meters, so it's 100 divided by 1000, okay, meters, times the resistance 0.25 plus the same 100 divided by 1000 times the reactance there 0.125, okay, and this is basically going to give you an impedance of 0.025 plus 0,0125J. Now this is the impedance of this section. Now we need to also find the impedance of this section, and remember it's 150 meters each, so it's the same impedance for that section. So it's going to be Z 150 meters. Okay, Z 150 meters is basically going to be R 150 meters plus XL, okay, 150 meters, and that's basically going to be equal to 150 divided by 1000 meters times the resistance 0,25 plus 150 divided by 1000 meters times 0,125J. Okay, there is a J here. Right, now this is going to be an impedance of 0,0375 plus 0,01875J. Now you need to convert this value into polar form, and this is going to give you a value of 0,042 with an angle of 26.56 degree ohm. Okay, impedance of this section and this section, and this section impedance is going to give you in polar form a value of 0,028 with an angle of 26.56 degree basically ohm. Right, so these are your impedance for your sections. Now that you've got the impedance and you know what the currents are, it's easy now to calculate your voltage drop. Okay, so I may even stop the tutorial here, and I'm expecting you guys to get the correct answers from here.